Right, let's restart this video by giving you another case where the general obviously has to be used. I'm considering a function f depending upon three variables x, y, z, and I call the output w. All those variables x, y, z depend themselves upon not one variable as before, but now two variables. So I have called the composition of those two functions. So first of all, the function that attach s and t, the two initial variables to x, y, z, I call it g. And the last function to apply on the left, I call it f. The composition is called phi. So at an input, a pair of point s of t, I associate the output w that depends upon x, y, z, but themselves depending upon s and t. Alright, so question, how can I compute the partial derivative of phi with respect to s, the partial derivative of phi with respect to t? Once I know those two guys, it is clear that I can define the differential phi with respect to, let's say, at a point st is nothing else than the partial derivative of phi with respect to s ds, and the partial derivative of phi with respect to t dt. Well, this is something that you already know. So these are the two objects I need to compute. How do you compute them? Maybe the best way to compute this is probably to write the differential of w with respect to x, y, and z. Let's do it. Actually, it won't certainly hurt to do that. dw, I said this is dw over dx times dx plus dw dy plus dw dz times dz. Right, so now what I'm going to do, I'm saying that should I want the partial derivative of w with respect to s, because this is what I want to know. What is the rate of change of w, the final output, when I change s infinitesimally by ds, knowing that t is a variable which is fixed? Well, what I could do, you know what? I can simply confuse for a moment the partial derivative and the total derivative. Means that, okay, I don't want to see those functions here depending upon t, but only depending upon s. Actually, that's the way we define partial derivative. We fix one variable and we let the other vary. So the idea is that I will divide everybody by ds. But which ds? Well, this is the thing. You could divide by ds here straight, and this gives you dw over dx, dx over ds, dw over dy times dy over ds, dw over dz times dz over ds, and give you a very similar formula that we have seen before with respect to one variable. I just want to say that essentially this is what you will do, except maybe that you will transform this writing by changing all those straight d by partial d's. So this writing, let's say, should be replaced temporarily by this writing, and then you divide by ds or dt, so depending upon which variable you want to differentiate. So let's say I want to differentiate with respect to t, and I would like to know what is d phi over dt, which is the same as dw over dt. Well, you see, you just take this expression and somehow obediently divide by this very abstract quantity, which is an infinitesimal quantity around t, and this gives you the expression of the rate of change, the partial rate of change of w with respect to t. Should you want to know the same formula with replacing t by s, well, no problem. You replace t by s here and you get a very similar formula. Now you may ask yourself, does the tree we have introduced before of any help? And I said yes. If you don't want to remember this scheme, this is perfectly all right. You can follow the scheme taken by the tree. So how does it work? Let me erase something here. I'm going to erase this part. Actually, I need to erase it a bit harder. Oh. Right, so what does the tree of rate of change tells me? It says that we have on the top the final output I want to consider. That's always where you should start. Where is the final output, sorry. Then, upon which variable does this final input depend in the first place? 3, x, y, z. Now, those variables, upon which variable do they depend upon? S and t. Alright, so this is the tree. A tree which has in total 6 branches. And I want to know what is dw or the ds. I'm going to get all the branches, let's say in a color that I can find someplace here. Hope this pen works. I'm gonna pick every branch where I see S. Okay, here this is a branch, and I'm going up in the trees up to the moment I'm gonna reach W. And I'm going to consider this branch. What does this branch? How am I going to translate this branch? By saying that this is dW of the dx. And you remember we multiply the rate of change. dW of dx multiplied by the rate of change of x with respect to s. But since this is now, it has to be a partial derivative because x depends also upon another variable. I cannot say straight dx or straight ds, but round dx over round ds. So like this. I've done this for x, you do exactly the same thing for y, and later for z, of course, dw or the dy, dy or the ds, dw or the dz, and dz or the ds. You have 3 different products of rate of change, you just add them. And you got absolutely the same formula as you got here. Should you want to look at the other branch starting by t, well, you will get a t instead. And that's the way you remember, that's another way to remember, let's say, the chain rule in this case where the final input depended upon 3 variables, and those 3 variables depend upon 2 variables. You could look at the formulas given, in the book. They give a more general formula where you have, let's say, n variable here, x1, x2, x3, xn, and you have m variable upon which x variable xi depends, so s1, s2 up to sm. This is pretty much the same formula. I mean, you wouldn't pretty much not. I don't think you will use a formula more complicated than this one in Calculus 3. Let's discuss an example just to illustrate what we have done. So I have assigned, I think, I'm not so sure, but I've assigned one exercise in the set of homework, which I think it's exercise, if I'm not wrong, it's exercise 7 on 14.5, yes. So, do I need this? Maybe I don't need this, but I'm gonna keep the tree. The tree is going to help me to remember everything. And actually, I'm going to erase and redraw it again. All right, so first of all, maybe I should state the exercise. So, yes, so we have this function x minus y, so let's call it w, equal x minus y to the power 5, where x and y equal s squared t and st squared. All right. So here the final input w depends upon only two variables, but if you know how to do it with three variables, of course you do know how to do this with two. It's even easier. So the tree looks like this. W depends upon only two variables. Those two variables depend upon s and t each. Alright, so now I can say that dw over ds, let's begin by this. This is equal to dw over dx times dx over ds plus dw over dy over ds. Well, I just follow pretty much, in my head I follow pretty much what the tree tells me. Or if you prefer, what I also so often do in my head is that I visualize the differential of w, dw equal dw over dx plus dw dy over dy, and then I know that I have to divide by partial s. Alright, so for this specific example, how can we simplify things here? You got 5, so dw over dx is simply 5x minus y to the power 4. And here I'm using the chain rule, but for a function depending upon one variable only, the chain rule and the power rule, in other words. Alright, multiply by dx of the ds. Dx of the ds is giving me 2st. So here I need to still further simplify because I can't allow myself to write an expression that depends upon x, y, s, and t. I mean, I need to simplify further here, but I will. Plus dy or the w over dy. So pay attention, this is going to be the same thing as we had before, but we're going to have a minus sign because the derivative of the input of the power is negative. I mean, the coefficient attached to y is minus 1 times dy over ds, but dy over ds is t squared. So this leads to dw over ds equal, okay, so you just replace, so times st, and the 2 becomes 2 times 5, that is a 10, minus 5, well, pretty much the same thing as squared t minus st squared times t squared. You can clearly simplify these things by saying this is s squared t minus st squared. So I forgot the power 4 here, sorry. To the power 4 times 10 st minus 5 t squared. Well, you could also factorize the 5 by 5t everywhere. Let's say I really want to make things neatly, so I would factorize this bracket, inside the bracket, by st and raise the factorization by 4. So this is going to be st to the power 4. Then the factor 5 I give here, and then the t here, times, what is it? S minus t to the power 4, and times, finally, s minus, so 2s, sorry, 2s minus 5t. And that's the best thing I can do for by means of simplification. Well, no mistake. I mean, when I ask you to compute a partial derivative like this, you guys can stop at this level. Unless I may ask you to simplify further as much as you can, but if I only ask you to compute the partial derivative of a certain quantity with respect to another variable. Well, I mean, this expression is maybe not compact, is maybe not as good as you learn in pre-calculus and whatnot, but you know what? Give me S and give me T, I should be able to compute this. So this final answer is fine. Let's do, for completeness, dw over dt, but it's going to be exactly the same thing, except that now the trees tell me that you should not divide by S but by T here, so let's put it in red. And of course the result is very different in this case, although there are some similarity, obviously have some similarity. We're going to have dw over dt equal dw over dx, or we already have computed this in the past, dx over dt and s square. Now plus dw over dy, we remember that it's minus 5xy to the power 4 times dy over dt, dy over dt is 2 times st again. So I won't be simplified further, but at least I want to simplify x and y by what they are. So this is 5 times s squared t minus st squared times s squared minus 5s squared t minus st squared. The 5, at least I can at least simplify this by 10. It really won't hurt. Times st, and you know what, as I said, you can leave the result like this. Right. You may say, would it be easier just to replace simply s and t, y by s and t here, and just to raise this by, could be possible that for this specific example, it's easier to directly compute this. However, remember, what makes the chain rule easier is that at a certain stage we are looking at partial derivative of dw over ds at specific values of s and t, and that makes the chain rule much easier. And also on the top of it, I mean, it's not only computing the general rule, but you will need to know those things for a more abstract approach of a lot of problems in mathematics, and not only, well, I mean, just replace s and t and we differentiate. We need to know those tools anyway, whenever it's for explicit computation or implicit and theoretical approach of every problem we're going to consider. And you will see later on we will need to carry out a lot of variables like that. Alright, so this is pretty much what I wanted to say about the chain rules. There is still one video that I would like to post, is the theory related to implicit differentiation and implicit function theorem. This is a quite interesting thing, and you will see there could be quite funny thing happening. We'll do that in a different video.